Good afternoon, everyone. I think some people moved in response to me talking, so yes, you can hear me. Great. Hi. For the attendance today, please tell me, what advice would you give your 10-year-old self? And yeah, 10 is not totally arbitrary, because I do have a 10-year-old kid. So I picked 10. So tell me what advice you would give your 10-year-old self. And I wanted to let you know we do have homework solutions coming soon. Those should be posted today, the ones that are not posted yet. I was not planning to post solutions for the lotting homework, but if you feel like you need them, let me know, and I'll put something together. But yeah, those should be posted today, the homework solutions. Do we have questions before we get started with midterm stuff?
Midterms on Thursday, right?
Midterms on Thursday. Okay. So on the As You Learn page in the week, where are we? Week 9? Week 8, my bad. We're in week 8. You will see that here we have listed midterm exam 311, 4 to 450. Exam details is what I'm going to click on here. So I emailed you all this information already, but just wanted to check to see if you have questions about any of this stuff. So I'll go through it real quick. So you're going to use As You Learn to access the exam, to like find the exam, and then to submit your version of it. And I will be in Zoom in the usual meeting room. So please log on to Zoom so that I know you're working on the exam. You don't have to have your camera turned on, but be available for chatting. Maybe we'll need to communicate something to you, like a typo or something. So be ready to communicate over chat. Any questions so far? Okay, so we're going to cover everything we talked about in lecture, excuse me, except for anything that uses the Gaussian tables. And we're not going to have a question about Chauvenet's criterion on this exam. Okay, but we will have questions about Gaussian functions. Just not any examples or problems, no problems like the examples that we did in class that include the use of a table, a Gaussian table. Okay, you can use whatever as far as book, notes, internet. Do not use other humans, including each other. You can talk to me. Okay, so those are our limitations for resources, references, etc. Okay. I will ask you to show work for certain questions, and I will let you know if you don't need to show work for other questions. So it should be very clear whether or not you need to show all those steps for finding that standard deviation or not, or whatever the example is, whatever that problem is asking for. So when I ask you to show work, you should be able to type it, with some sort, with like, still using proper math, but using like SQRT for square root, in parentheses stuff. Or you can do handwritten work and submit that, or you can do it in Jupyter Notebook and make it beautiful and submit that, but it needs to be a PDF. I don't really care what you use. It has to be a PDF that is legible. I might ask you to make some graphs. So if you use Python or Excel or other software to do graphs or calculations, I would like you to include a PDF of that code and or spreadsheet. Python is preferred because then I can like tell if your code is wrong or not. If you're using some obscure software, I can't give you as much partial credit, but I'll try. Okay, and then graphs, you're going to be making graphs and you might have to do a linear curve fit or a Gaussian histogram fit. So if you don't have a way to do that, let me know. We need to solve that problem sooner than later. And again, you can use whatever software you want to do that, but I would prefer if you could use Python, because then again, I can troubleshoot it, or not troubleshoot it, but see if there are if there's stuff there for me to give you partial credit. MATLAB is okay too. I can do that also fine. Questions?
Dr. Hester, would you be willing to like post a YouTube video of how to do like a Gaussian fit in like Python?
Oh yeah,
Because
that's a
I'm
good
still
idea.
very unsure.
Sure. Yeah, I'll do that. That's a good idea. Thank you for the suggestion.
Okay, thank you.
With submitting PDFs, like, would we have to submit all the PDFs within the test time?
That would be preferred, but if you need more time, just let me know and it will be okay.
And is it like one of those things where like, because I have I'll ask you later. I'm not sure how to ask a question right now.
Okay. The easiest way to convert to PDF is, I just forgot the name of it. You can use your phone to take a photo and it automatically makes a PDF of the photo. Cam
The
scanner.
Cam Scanner app.
Yeah, Cam Scanner. So that makes it real easy.
Well, I mean, I have a scanner that works pretty well, but it's just
Okay.
that it only is really, I have an app that's only really compatible that's not on a Windows computer. So
Okay, well then the backup plan should be cell phone Cam Scanner. Yeah, I don't want this to be a big deal with the uploading and stuff. So you just let me know if you need more time for that. You can also, if you're really like having anxiety about it, you can just put everything in a Google Drive and send me the link. And then also put it on As You Learn eventually, but I want it on As You Learn as a record of your, submission of your work, a formal record. Other questions? Okay. Alrighty, let's do this review. I put together a review document here. So you can go along in this if you want on your own. I'm going to show the actual PowerPoint here to just make the viewing the best, hopefully. Okay, whatever. We'll just do this. All right, so I tried to condense everything that you will need for this midterm into this one document. It doesn't have everything explained, obviously, but the important concepts are listed and the main equations that you might need. So let's go way back to graphs. This was a while ago. So these are the exact slides out of your, the presentations that I did in class. And I'm going to expect you to know the rules for a good graph. So we have an excellent example of a graph here. We can't see the error bars. That's one issue. But maybe they just don't have any. Otherwise, we need to have our graphs need to be explained. And so that is done in a figure caption in a paper or a title in a presentation or in a non-paper situation. And that title or figure caption should be clear and uniquely identify and explain the graph. So you put your independent variable on the abscissa, the horizontal axis, and the dependent variable on the coordinate on the y-axis. Scale should be easy to read. You should adjust your scale and put prefixes or times 10 to the whatever in your units, like this person did here. They didn't write 200 times 10 to the minus 9, 240 times 10 to the minus 9, and have meters here. So that's another factor. All right, you don't have to show the 0. Your intersection here does not have to be at an actual 0. It can be kind of adjusted to make your data fill up the space well. Tick marks need to be there, excuse me. And your axis labels need to be words with units. You want to use small symbols so that you can show your error bars. If your symbols are huge, they're going to cover up your error bars. And if you do a fit, always include the equation with the proper units and symbols. Okay. I'm going to assume if there's not questions, just, shout out if you have a question. Okay, for significant figures with uncertainty, we have a few rules. The precisions should match. Rule number 1, the number of numbers after the decimal of my value should be the number of values after the decimal of my uncertainty. And rule number 2, I should only have one sig fig in my uncertainty. So this expression shown above would be not appropriate. We would take that expression and cut the uncertainty down to 1 sig fig and then make our precision of our value match so that we have 2 numbers after the decimal for both.
Isn't the uncertainty supposed to be always rounded up?
Yeah, that's just 1 sig fig. Oh wait, I see what you mean.
Like instead of 0.02 kilograms, it would be 0.03.
Yeah, I guess that's true. In this case, I'm going to change that. That is the most safe thing to do. In this case, the most conservative thing to do. Yes. Thank you, Tristan. I think that was Tristan. Anybody else? Questions? Okay. What is up with this slide? Okay, I don't know why that happened. All right, I put everything here together on one slide as far as error propagation, uncertainty propagation. On the left, we have our values being calculated. Q is our calculated value from measured quantities, X, Y, and Z. That should be green. So we have a measured quantities X, Y, and Z in green, and then Q is the calculated value that we use, that we find from those measured values. And then on the right, we have the corresponding uncertainty in Q based on the uncertainties in the measured quantities. So we haven't really ever had this all on one slide before, in one place before, I don't think. Maybe on that, there was something I gave you that maybe had something like this on it. But here it is anyway, all together. And if you look carefully, you'll see that this general equation for error propagation, for uncertainty propagation, is basically equivalent to the rest of these for those specific cases. The only place it's kind of different is with this quotient rule, but you're going to end up with a really, really similar, if not same, uncertainty in Q, whether or not you use this equation for a quotient or this equation for a quotient. So for example, if we look up here, we have a sum of x, y, and z. That means Q is a function of x, y, and z. So we could use this equation to find delta Q. And then, you know, if you look up there, delta Q, delta X is 1 for that equation at the top. Delta Q, delta Y is 1, and delta Q, delta Z is 1. So we end up with the same equation on the top here as we would with the bottom one, with the general form. It's just a little simpler maybe to go with the, maybe less mistakes, I don't know, with the specific equation. But the general form is always going to work. Again, here, if we use the general form for this, our delta Q is going to be the derivative of b times x, so that's b, times delta x. So we would have a b here, capital B, and then a delta x, and then quantity squared. So we would still end up with this result because there's no y and no z there. So if you go through that for the exponent and the function of x, q function of x, you're going to see it's the same as what you would get from that general form. Questions about uncertainty propagation? Okay. Alrighty. Okay. This is a big, important topic for senior seminar, and then, you know, just when you go out into the world and become a professional scientist or engineer, understanding error as far as random and systematic is important. So we've gone through this a bunch of times. I'm not going to go through this slide again, but I do want to emphasize that if you can take a whole bunch of measurements over and over again, you can reduce your random error. You can make your random error better. If you can, you know, repeat over and over and over, that will help with the random error. That will not help the systematic error. For the systematic error, you have to figure out what's going on and fix it. Or at least account for it, like know how much to account for it. But systematic error is something you want to figure out what it is and go back and fix it. You can't really ever fix the random error. You can just take a lot of measurements. And the more you take, the better your uncertainty is. But to get rid of your systematic error, you have to fix it, you know, and then do the experiment again. Okay. So if you take n measurements of the same thing, let's say we're trying to reduce that random error, and we're taking n measurements of the same thing, then we're going to, let me make that clear. This thing is x sub I. So this is, you know, n measurements of this. In this case, we'll, I guess, think of it as a length, since x is usually a length. Okay, so we're taking n measurements of this same thing over and over and over a whole lot of time. The uncertainty in x sub I is going to be the standard deviation, which is shown here, this equation. So it's basically the residual squared. So it's the current value for I minus the mean of all the values measured for x sub I. If we take that and square it and add those up for all the different i's, and then multiply by 1 over n minus 1 and take the square root, we have standard deviation. That's going to be our uncertainty in our measurement x sub I for n measurements. Again, I want to emphasize both random error and systematic error are occurring during those n measurements. And we can decrease the random error by increasing n, the number of points. We can make the standard deviation smaller and the uncertainty in x sub I smaller by increasing n in this denominator here. We cannot help the systematic error by increasing n. It doesn't do anything. This does nothing to the systematic error. But we can decrease the random error by increasing n. Questions, anybody? Comments? Okay. All right. We can also go a little further and we can find the uncertainty in our mean with this framework. The uncertainty in the mean of all those x sub I values is called the standard deviation of the mean and is sigma sub x with the bar over it. And that's going to be your standard deviation that we calculated on the previous slide here, divided by the square root of n. So again, you can decrease your uncertainty in the you can decrease the uncertainty in your mean by increasing n. And you're going to decrease it by a factor of square root of n. So n needs to be very large in order for your uncertainty in the mean to be affected. In a positive way, a significant way. Okay, so that's the standard deviation of the mean. That's different from the standard deviation. Two different things. So sometimes you'll see standard deviation of the mean written as SDOM. So if we want to find our random error and like quantify it, we can use this standard deviation and standard deviation of the mean to quantify what is the random error in our measurement x sub I. That doesn't help us quantify the systematic error necessarily, might help, but this is specifically for the random error, the error that gets reduced if you increase n. That's what the random error is. It has to be truly random for that to work out. Let's say we're measuring many different categories of things instead of the same thing over and over. Before we were measuring the same thing over and over, x sub I, x sub I, x sub I, the same length over and over in the same way every time. Everything was the same with those measurements as far as we knew when we were doing them. Now we're doing n measurements of a whole bunch of different things, a whole bunch of different categories of things. So we're doing x sub I and y sub I and z sub I and lots of different sub I's. Here's an example from Wikipedia. So we have here the number of incoming links to articles in the English Wikipedia from other articles. So let's say we have a Wikipedia page. If it has 0 links to other Wikipedia pages, it would be in this category. And if it has 1 link to other Wikipedia pages, it would be in this category. And if it has 2 links to other Wikipedia pages, it would be in this category, and so on and so forth. So we end up with what's called a histogram once we plot all of that data. Is this a Gaussian curve? Does that look Gaussian to you? What do you think?
It looks more like exponential decay.
Yeah.
Okay. But what if I like kind of centered my Gaussian over on the left-hand side or something?
Yeah, I could see it.
Okay, anybody else? I mean, let's just keep going. So I don't think this looks Gaussian. I think y'all were right with your initial answers before I was like, well, yeah, maybe. Yeah, this does not look Gaussian to me at all. First of all, it's got this curvature here that's like concave, that's really concave the whole way, and there's kind of a change in concavity with a Gaussian that you should be able to see, where it looks kind of like this curvature on the top and then like this curvature at the bottom. Also, we can't see the whole thing, and there's no such thing as like negative incoming links. So we're missing half the Gaussian, which seems weird as well. So I agree. Let's keep going. So there's two kinds of histograms that we've discussed in this class: bar histograms, bin histograms. The difference is just how you're setting up the histogram graph. So with bar histograms, every single category, I guess you could say, has the same width. Like each of these has a width of 1. On our histogram here, there's 1 number. And so you're going to have the same width of each column in your histogram for a bar histogram. So the number of columns is also called the number of bins, and that's k. And f sub k is the fraction of results out of n in your bin k, out of big N, total number of measurements. And little n sub k is the number of results in bin k. So it makes sense that big F sub k, the fraction of results in bin k, is going to be the number of results in bin k divided by the total number of results or measurements. F sub k is also the height of the bar in the histogram. And if we sum all of the F sub k's together, we should get 1, which is the normalization condition. Basically, the area under the curve is 1. Okay, under the, not curve, area under the top of the histogram. Okay, so a bin histogram is different because we can have widths of our bins or columns, whatever you want to call them. Those can be different widths. In bin histograms, both the height and the width, delta k, are going to matter. So now we're going to have a delta k and the equations to describe the bin histogram, where we didn't have that before. The math is pretty much the same, similar. We have our, we still have our normalization condition that the fraction instead is now this area where we have f sub k, the height, times the width, delta k, as our area per bin. And then we add up all those areas and those are equal to 1. We can also find an average value, x sub average, by multiplying each result, what they were calling it last time, or measurement, times its corresponding fractional value, add those up, and we get our average value in our bin histogram. So histograms, let me go to this slide actually. Histograms have these equations we were just talking about. So this is for a bin histogram. And the mean of our measured values is going to be the original definition that we stated at the beginning of class. So we add up all the x sub i's from 1 to n and divide by n to get the mean, or we can use this framework to get the mean. If we look at this framework, it's easier to extrapolate to the distribution functions. And we still have our definition of standard deviation. That's still going to be true for our histograms. It's still going to be how we find that standard deviation. And what we want to realize is that for histograms for extremely large n, these histograms are going to become, they're going to start looking continuous. So if we had 8 million categories here across the x-axis, this would start to look a lot more like a curve and a lot less like a bunch of bars. So like, kind of like is shown here. So we have these curve, like continuous versions of the histogram equations and histogram properties, but we have a continuous version for when n is very, very large. Or we can think of these distribution functions as a good way to model the histogram, even if n isn't super huge. So the first one we can look at is here. We have the sum of a bunch of areas under the curve, adding up to 1, and areas under the histogram, basically adding up to 1. That makes sense that the equivalent continuous version of that would be an integral over all x of the height, basically, of that function as a function of x. We integrate that with respect to dx, and that has to add up to 1. So this is the continuous version of this more discrete expression. Questions so far? All right, so then we have, here's a chunk, like one bin of my histogram has this area, f sub k, big F sub k. And that's going to be the height of the bin times the width of the bin. So that's basically the area under the curve of the histogram, you know, in this region, delta k. The continuous version of that is going to be the area under the curve of f of x, this function of x in the x direction from a to b. So a to b is the same width as delta k. And we do that, we perform that integral, and we're going to get the same outcome. We still have an area. We just have a continuous version here. Same thing again with our definition of our mean in terms of that f sub k area of our bin. We can take each measured value and multiply by the bin area, add all those up to get the mean in this discrete way, or we can multiply x times the function f of x that's describing the area in the histogram, and integrate that from negative infinity to infinity, and that's going to give us an equivalent average value. Okay, the variance is a little different. It is defined as the function times this it's called the residual, just to remind you, squared, and then we integrate that from negative infinity to infinity. So the continuous version of your standard deviation is defined a little differently, but still pretty similar. Questions? All right, so this is the last slide and the last kind of topic that you would need to know about for the midterm. You need to understand what is a Gaussian distribution, what is a bell curve, what is a normal curve, a normal distribution. So a Gaussian distribution is what results if you're measuring something that has only random error, basically. If all systematic error has been removed, then, and you're measuring the same thing over and over and over, then you will end up with a Gaussian function, a normal distribution, a bell curve. So the system has to be truly random, and, the errors involved have to be relatively small. So what that means as far as small is, like, we couldn't have a bunch of data happening the deviation in your random system, randomly acting system, can't be very large. So for example, with the optical tweezers trapping the object, and there's Brownian motion moving it around, and that Brownian motion is totally random, the distance from equilibrium is incredibly small. And so that helps to ensure that it's a Gaussian distribution. Okay, so the equation that we use to describe a Gaussian function is shown here, e to the minus x squared over 2 sigma squared. So if you have this general form where it's e to the minus x squared with like a constant involved in the exponent, then you have a Gaussian function. Of course, you can shift this Gaussian function around. You can add or subtract from the x here to shift your Gaussian in the x direction along the x-axis. And you can add, some value to this function to shift it in the along the dependent axis, and so on and so forth. But you need to have this general form in the first place if you are describing a histogram or a system as a Gaussian system. So you have to make sure first that it has random errors that are only random and small. Okay, so this function that we are showing here doesn't have anything added to it. So if it's going to be centered at x equals 0, and when we substitute 0 for x, we're going to get 1 back. So the height is 1. And it is not normalized necessarily like we had for our bin histograms and our bar histograms. So I am going to expect you to know how to fit this Gaussian distribution. I will put a video up on that as you learn with examples of how to do that, or at least one example. And you will need to figure out the standard deviation from the fit. You will need to figure out what that standard deviation is from the fit, and then be able to interpret that, what that means, basically. What is that standard deviation? And how can I use that to describe a random system, a truly random system? Okay. Questions? Anyone?
Would redoing homeworks be good practice like this?
Say that again, sorry.
Would redoing homeworks be good practice for the test?
Definitely. But some of the homework problems, take a little longer than what would, than what you can really accomplish on the test. So my intent is to be able to test you on all these concepts, but not have to take a lot of time as much as you would on a homework problem. Other questions? Okay. Well, this is posted. This review is posted on the As You Learn page. You can obviously use this review during the exam, but you are still going to have to work quickly, so you don't want to have to rely on this necessarily. It would be better to practice a lot of things and not even have to look it up. Of course, there is still a lot to memorize and remember, so being able to look it up is an option.
I have a quick question.
Yeah.
In the earlier of the presentation, you gave how to do the uncertainty of addition and division and stuff like that. Is there or will there be a question on the midterm where we can't use just the general form? Will we be forced to use one of the other ways to find the standard deviation?
Yeah, so the general form should always work.
Sure.
I'm not going to tell you what to use. I'm not going to force you to say use general form. And if you have a quotient situation, you can use this method or the general form. Both are correct.
Okay.
I think I answered your question, Tristan.
Yeah, you did. Thank you.
Okay. Other questions? Okay, well, I'm going to give you 5 minutes to start studying. So go have a nice study session. And I will see you Thursday.
Have a great day.
You too. Thanks. Bye, everybody.